recording my lectures as I go. So on those days you're absent, you can get them. So I'll have my voice over the top of it, so you'll see the screens and hear my voice. Okay. So fact is, yesterday's is already up there. So it's not perfect yet. Still got some watermarks, but I'm trying to make it so that it's accessible for you guys, in case you want to go back and review what the heck was he talking about in class. Okay? That's my plan. They're in the locker for this class. They're by date. So as we go, that locker will fill up, I guess. There's one actually in the locker. There's one that says notes, and in there you'll find the MP4s, the video files. Okay, we have studied polyatomic ions before, and that piece of paper I just gave you, and some of you put away, you probably want that because on the back of that is a list of polyatomic ions. Okay, we have talked about polyatomic ions before. They were groups of atoms that stayed together and had a charge. We did them last chapter. That's where you encountered them in the first place, was last chapter. And we built them last chapter. That's all we did with them last chapter. We said, how does this form? So it was the things that were covalently bonded with either extra electrons or missing some electrons. And so last chapter, we learned that there were groups of atoms that did this. Today, we're going to learn how to write their names and use them in formulas. Okay. Good news, you don't have to memorize them. You'll be provided with that list. You're just going to have to recognize that you need them. Okay. So you've got the list there. I'm going to go through a few of them and talk about how they're related to each other. They're not a bunch of random words. Okay. Actually, the first one on the list is probably the most complicated one, acetate. Okay. It's what gives vinegar its taste. The acetate ion. Okay. C2H3O2. Guys, stop and think. I just gave you a list of polyatomic ions. I told you I would provide you with the polyatomic ions. Why do you feel so dedicated that you have to copy them as I put them on the screen? Okay. Members, the notes are for you, not for me. Are you going to go back home and go through your notes and look for the polyatomic ions? No, you're going to pick up that yellow paper, right? So stop and focus on relationships. That which is what you write down, but copying these down won't do you any good because that'll just give you that yellow piece of paper again. Okay? I already gave it to you once. Okay. Nitrate. And what you'll see is a lot of these polyatomic ions end in ATE. Okay? And a lot of them, the first part tells you what element is next to that it's got, and ATE means oxygen. So nitrate means nitrogen and some oxygen. Acetate's a little bit more complicated. They thought there was a different element. Turned out it wasn't an element. It fell apart. Then there's nitrite. Nitrite, the IT ending, also means oxygen, but it means one less oxygen than the nitrate. So you got to be careful whether it's ATE, ITE, or IDE. Look at those endings, becomes really important. Okay. Hydroxide, again, is an IDE. Most of the rest lived in ATE or ITE. Hydroxide, they named it that way because they thought it was an element for a while. And can you tell they named it backwards? Wouldn't you call it oxhydride? The O's first. So they call it hydroxide. Permanganate, ATE, it's got manganese in it. The other one that doesn't end in ATE is cyanide, because they thought that there was an element. That cyanide was part of an element. And CN with the 1 minus. So that means 1 carbon, 1 nitrogen bonded together. We drew that one a couple times last chapter. Okay. Then there's a whole bunch of ones with ClO in them. Okay. They all into that TE at the end. There's my root one. I think of ATE version as the root. And then I've got with 1 less oxygen, the chlorite. And then to a chemist, the prefix hypo means even 1 less oxygen. And per means 1 more oxygen. So chlorate has 1 oxygen, chlorite has 2, hypochlorite has 1. Perchlorate has 1 more, which is 4. Okay. And those patterns fall up there. So if you look at your yellow sheet, there's also bromate on the list. You see bromate there? What would bromite be? 1 less oxygen with the same charge, right? It would do the same thing this does. And hypobromite would be 2 less oxygens than a bromate. 1 for the ite and 1 for the hypo. And that's how those work. I know there's some with hydrogens. We'll talk about those in just a second. Okay. Then in the 2 negative ions, sulfate, SO4 with the 2 negative. The next one is sulfite, SO3 with the 2 negative. Then there's carbonate, ATE. Han Solo was wrong. There's no such thing as carbonite. He couldn't have been frozen in it. And chromate is chromium with some oxygen. Dichromate is almost twice the size of chromate. It's twice as many chromiums, almost twice as many oxygens. See that? Silicate, SiO3. Now you'll see on the other side I got things like hydrogen sulfate. Well, it's still sulfate, SO4 with a 2 minus, but you stick a hydrogen ion in front of it, and the hydrogen ion is 1 plus. So hydrogen sulfate doesn't add up to 2 minus anymore, it only adds up to 1 minus. That's why it's on the 1 minus column. You see hydrogen carbonate over there, hydrogen sulfate? Hydrogen carbonate works the same way. So the hydrogen just lowers the charge by 1. Then there's phosphate and phosphite. Then there's hydrogen phosphate, which is one hydrogen stuck on, and dihydrogen phosphate, which is 2 hydrogens stuck on. And then there's a couple that are positive. The ammonium ion. Somebody's going to be looking on the periodic table trying to find ammonium. It's not on there. You think it is because it ends in -um. The reason why they let it end in -um is because it's positive. Okay. So it would show up first in a name and in a formula. Positive piece gets written first. And the mercury 1 is polyatomic. So if mercury has a charge of 1, it comes in packages of 2, just like oxygen, nitrogen. You don't have to memorize that list, you just have to know to flip it over and look at it. Okay? Because if I've got polyatomic ions, I don't have just 2 kinds of compounds. So now we're ready to take the notes on ternary ionic compounds. Binary was 2, ternary is 3. 3 elements. And if you're going to have 3 elements, the only ones we can name are the ones that have polyatomic ions. So from the formula, you'll be able to tell because it'll have 3 capital letters, at least 3. Okay, so when we want to name chemicals with these polyatomic ions in them, the rule is the same as the rule yesterday. Same as the answer to 14. Write the name of the cation, then the name of the anion. Except now one of the names is going to be the name of the polyatomic ion. You still just name the ions. What ions are there? So we're not changing that piece of it. Name the ions. So if I wanted you to name NaNO3, same kinds of decisions you made as you named them before. Na is sodium. It's a metal. With metals, I have to ask myself, does that need Roman numerals? Sodium does not need Roman numerals. NO3, 2 capital letters. Means I'm not supposed to memorize it. Means I'm supposed to flip over the yellow piece of paper, find on that yellow piece of paper, say that NO3 is called nitrate. That's it. It's made up of sodium ions and nitrate ions. That's all there is to it. So we're not doing anything different, just a big piece instead of a small piece. Okay? So we're not really adding anything on to what we were doing before. Okay. CaSO4. I find Ca on the periodic table. It's a metal, so it's ionic. Well, the polyatomic ion is covalently bonded together with some extra electrons, so it has a charge. I had to get those electrons from a positive piece. So we just didn't try to show the dots all moving, because that gets ugly. Trying to moving and sharing. Oh, our model doesn't do a good job of showing that. And Ca is calcium. Does calcium need Roman numerals? In group 2A, doesn't need Roman numerals. SO4, 2 capital letters. So that's sulfate. So the name of that is calcium sulfate. Now, you'll notice they end in 8s. If you pick up any ingredients list on a container, you're going to find a lot of things that end in HEE. All those things that end in HEE are polyatomic ions. Our list is not exhaustive. There's a lot more polyatomic ions than the ones I've given you. So recognize them by their endings. What about CuSO3? Well, Cu is copper. Does copper need Roman numerals? Yeah. Copper's in the middle of transition metals, or right there in group, the last column of the transition metals, next last column. So it needs Roman numerals. It's not 1A, 2A, or 3A. SO3, well, if SO4 was sulfate, then SO3 has to be sulfite. Now, what number do I put there? I got to figure out the charge on copper. Well, I know sulfite is 2 negative, because I looked it up. That means this whole thing is 2 negative. So my total negative is 2 negative. So my total positive has to be 2 positive. I only got 1 copper. What's the charge on that copper? 2 positive. And that 2 is what goes here. So it's copper to sulfite. Now, what's going to happen, what you're going to be tempted to do, I'll show you why it's wrong. You're going to say, oh, sulfite is 2 minus and I have 3 of them. Do you have 3 sulfites? So it's good to think of them as a package. Think of them as in parentheses, the polyatomic ions. Because that's what we did when we drew them, right? We drew the picture, then we put the charge outside. Somewhere in here, there were some extra electrons. That's what we're trying to describe. With SO3, 2 negative. Okay? The heck is that? NH4 in parentheses 2O. See 3 capital letters. But that first thing is not a metal. So it's not a metal, but it's positive. We've only got a couple of things. Or I've got one thing that's not a metal and it's positive. It's on the back side of my periodic table. It says NH4 is called ammonium. Remember we had the one positive polyatomic ion, ammonium. O is oxygen, but it's negative here, so we change it to oxide. Ammonium oxide. That's the name, following our rules. But, whoa, Mr. Green, what's with all those parentheses and stuff? Why is that there? Well, let's try to go backwards. If I want to do ammonium oxide, I put ammonium, NH4 plus, next to oxide, O with a 2 minus. Does that add up to 0? No. So I want to do my crisscross. So I put the 1 next to O. That doesn't do me any good. But when I go to put that 2, do I want to say NH42? Do I want to say just NH2? No, it's still NH4. That NH4 stays together. I need 2 of the NH4s. The only way I can write 2 of the NH4s is with parentheses. See, NH42 doesn't work. NH2, I don't want to lose the H's. That would change what charge I had. So I want to keep all 4 of those H's. I need 2 things that are positive. The positive piece is NH4. NH4 plus and NH4 plus. Okay? FeOH3. Fe is iron. Iron. Okay, iron. Right in the middle of the transition metals, so that tells me that iron needs Roman numerals. OH is 2 capital letters. It means it's probably on the back side of my periodic table. And that is called hydroxide. And so it's iron something hydroxide. I just have to figure out what that hydroxide is. Well, hydroxide's 1 minus, and it took 3 of them. So I've got 3 negatives and only 1 iron. How positive is that 1 iron? What's going to make it equal 0? Well, I got 3 negatives. What's going to make it equal 0 is 3 positives, so that iron has to be 3 plus. What's iron 3 hydroxide? Again, Mr. Green, what is with the parentheses? Can't I just write FeOH3? Is that the same thing? That says 3 H's and only 1 O, right? I want 3 O's and 3 H's. So I want 3 OH's. That's the need for the parentheses. I have 3 of those pieces. Multiple polyatomic ions get put in parentheses. About LICN. Li is lithium. Does lithium need Roman numerals? CN, it's on my list, 2 capital letters. It's called cyanide. So lithium cyanide. Extra hard? Still the same stuff, right? The hard part is figuring out the Roman numerals. Okay? Going the other way. Name of the compound is just naming the ions. So what ions? Oh. So let's go the other way. Write the formulas from that. So I just need to know what the ions are and make them equal 0. So copper 2 sulfate. Copper is Cu. I look up at the periodic table. It doesn't tell me anything about its charge, but I need to know its charge. What's the charge on copper? It's 2. That's what that 2 is. That 2 is the charge. Sulfate ends in ATE, so I know it's polyatomic. It's SO4 with a 2 minus charge. That add up to 0? 2 plus and 2 minus adds up to 0. So we're done. So it's CuSO4. Same stuff, right? Equals 0, we're done. If it doesn't equal 0, we crisscross. About gallium nitrate. Now, there's a big hint here. Gallium doesn't have a Roman numeral. That gives you a hint about where to look for it. You should look at 1A, 2A, and 3A, right? And you'll find gallium is in group 3A. So gallium gets a 3 plus charge because it's in 3A. 3 plus. Nitrate ends in ATE, NO3 with a 1 minus charge. Does that equal 0? And some people are tempted to say, oh, 3 negative 1s equals 3 negative, 3 negative, 3 positive. But no, no, no. I don't have 3 negative 1s. I've got 4 atoms that are negative 1. And I need 3 of those. That make sense? That's going to equal 0. And I need the parentheses. Each NO3 is 1 negative. I need 3 of them. So the parentheses says 3 NO3s. Right? How nasty can I get? Well, I could ask you this one. Ammonium chloride. It doesn't have Roman numerals, so you look up and down, group 1A, 2A, and 3A, and you can't find ammonium anywhere. Why not? Because it's on the back of the periodic table. Ammonium is NH4. And 1 plus charge. Chloride. Well, it's an IDE. So that means it must be off the periodic table. Cl is in group 7A. 7A makes a 1 minus charge. 1 plus and 1 minus. That equals 0? Yep. So it's just NH4 Cl. That's all there is to it. So we're not jumping huge distances with these polyatomic ions. Just another place to get an ion from. Okay? So things to look for. The most common mistake is people want to use those Roman numerals as how many there are, not as the charges. Okay. That's why they write as Roman numerals. Okay. If the anion ends in IDE, it's probably off the periodic table. There's only 2 exceptions to that, and that is cyanide and hydroxide. And cyanide and hydroxide, their name almost spells what's in them. Hydroxide, that's a hydrogen and an oxygen, OH. Cyanide, CNN, carbon and nitrogen. If it ends in ate or right, it is polyatomic. And just because I saw a few people doing this and I want to break the habit right away, in both the name and the formula, the positive piece always gets written first. The name of the formula. Okay. And that leaves us with hydrogen. So I don't know, on the stuff you turned in yesterday, I don't know if you noticed, recognized that sometimes it was called the hydrogen ion and sometimes it was called the hydride ion. Because hydrogen can act like a metal and lose its electron and make H+, and it can gain an electron, look like helium, and make an H-. So sometimes it makes an H plus, sometimes it makes an H minus. How are we going to know which one it's doing? Well, the answer is, depends on where it's at in the formula. If it's first, it's acting like a metal. It's hydrogen. If it's second, it's acting like a non-metal. So it's hydride. So it depends on where they put it in the formula. If they put it first, it's hydrogen. If the second is hydride. Makes sense? Okay, so this should be pretty self-explanatory. On the front side, I give you the names of the ions, then ask you to figure out their charges and figure out the formula for the compound and its name. Or then I give you a couple of ions, you can name them, figure out what the compound is and write its name. Then I give you the name, which means you can figure out what ions there are, so you can figure out what charge there is, what the formula is, and what the name would be. Right? Does that make sense? I would do the front side before I did the back side, because it'll get you used to going how the pieces go back and forth between those two things. And I will tonight, actually while you guys are working on this, I will post the ones on the left-hand side, okay? Not the ones on the right-hand side. So work down the left-hand side first, and then check the answers. See what mistakes you were making there. That make sense? Before you flip over and see if you can make fewer mistakes on the right-hand side. Seem like a reasonable approach? Okay. Because I have just put the answers out for all of them, and people just copied them and didn't learn anything. So that's why I want to see those two. That's it.